The other reaction that we have in 9.8 is halohydrin formation. It's very similar to the halogenation reaction, which is why they're in the same section. The halohydrin formation reaction has a halogen, again either bromine or chlorine, with water as the solvent. And in this reaction, we will add one halogen, bromine in this particular case, or chlorine if we were using Cl2, and an OH group instead of a second halogen. So the conditions of this reaction, again, whenever we do addition reactions, we always want to think about three conditions. First of all, Markovnikov's rule. In this reaction, we don't have hydrogen, so Markovnikov's rule doesn't apply. However, we do have to consider, we're adding two different things, a bromine and a hydroxyl group. We do have to consider where each of those groups will go. So we have a pseudo-Markovnikov's rule. It's totally not called that, but I'll put some quotation marks around that because it's not a real Markovnikov's rule. The hydroxide ion, the OH, goes on the most substituted carbon. And the rationale for this is the same as what we see with Markovnikov's rule. When we look at the mechanism, it'll make sense as to why the hydroxyl, the OH group, goes on the most substituted carbon, and it's very similar to how we explain Markovnikov's rule. Again, we have no rearrangement in this reaction. It does go through the bromonium ion or the chloronium ion intermediate. So there's no opportunity to see any sort of rearrangement, and we get anti-addition just like we saw in the halogenation reaction. For the same reason as we saw with the halogenation reaction. So let's look at a couple of examples with mechanism. We'll keep it simple. Look at the same reactions that we did in the halogenation. We start just the same way that we start the halogenation reaction. The double bond attacks the halogen. We get a bond to the chlorine, this weird intermediate. We have a chloride ion that is created when the chlorine-chlorine bond breaks. In the halogenation reaction, the chloride ion is what attacks the carbon and breaks the carbon-chlorine bond and gives us our product. However, in the halohydrin process, we have water present, and water is a better nucleophile than the halogen. So instead of the halogen attacking the carbon, we're going to get a water molecule attacking the carbon. And in this particular molecule, because of the symmetry of the molecule, the water molecule can attack either side. They're both going to be just as likely, so we don't have to worry at this point about the pseudo-Markovnikov's rule. And also, I didn't do a very good job of drawing. Kind of want to redraw. Just like we saw in the halogen reaction, the water molecule is going to come from underneath the chlorine to give us our anti-arrangement. So we're going to get something that looks like this. And then we simply need to deprotonate the water molecule that was just attached. We'll use another water molecule for that deprotonation. And that gives us our halohydrin product with an enantiomer also because we could be attacking from the other side, always a possibility. If we want to insert stereochemistry into this, we're going to use the same strategy that we saw with the halogenation. We're going to say the methyl groups are both on the same side of the double bond. They're syn to each other. So when over the course of this reaction, they're going to end up pushed anti to each other. So we'll do something like that, and that will let us have our OH group and halogen anti to each other as well. Here is another example. Again, the double bond is going to attack the halogen, break the bromine-bromine bond. We're going to make the intermediate and a bromide ion kicked off. In this particular case, in the next step is the water molecule attacking the intermediate. And in this particular case, because we don't have a symmetrical molecule, we're going to apply this Pseudo-Markovnikov's rule. The hydroxide is going to go, or in this case the water molecule is going to attack the most substituted carbon. So we're going to see attack over here in this site, again from underneath, breaking that particular carbon-bromine bond, and we're not going to see it hitting on the other side. The reason that it attacks in this particular site is that before the water molecule attacks, or as the water molecule is coming into attack, the carbon-bromine bond is beginning to break. And as the carbon-bromine bond is beginning to break, the positive charge that's on the bromine right now gets shifted down onto this carbon as that bond is being released. Or if it was breaking from this side, it would be shifting down onto this carbon. It's more stable to have the positive charge, or the pseudo-positive charge, down on this carbon because it's a more substituted carbon, and it would be a more stable carbocation if it ever got to that point. It will be less stable to put the positive charge on this carbon because it's not as substituted. So it's the same kind of concept as Markovnikov's rule. It's going to break the carbon-bromine bond. It's going to break at the point that has the most stable and substituted carbon atom, and that breaking point dictates where the water molecule attacks. So we get this as our next intermediate. We're going to deprotonate it. Methyl group, and we have to consider our stereochemistry. The bromine and the OH group need to be anti to each other, and the two methyl groups, which were initially on the same side, they need to be anti to each other now as well. And we're going to make the other enantiomer of that. Let's do one last example without a mechanism. In this particular case, if we just do it real quick without a mechanism, here's our initial molecule. We're going to put an OH group on the most substituted carbon of the alkene. We're going to put a chlorine on the other carbon. We want to make sure that they are anti to each other. And we're going to throw stereochemistry in on that carbon as well. And we make the enantiomer. Hopefully that shows up in the video. That's a dash. It looks like a very wedgy dash. This one is a wedge. Practice this with conceptual checkpoint 9.26, skill builder 9.6, and problems 9:27 through 29 and 73. That is practice for both halogenation and halohydrin formation.